The legend of the falling apple serves as a popular anecdote illustrating Isaac Newton's groundbreaking discovery of gravity. Observing this simple phenomenon, Newton recognized that a force must be acting upon the apple, causing it to accelerate towards the earth. He termed this force gravity. Newton's genius lay in his realization that gravity is not limited to earth alone. He postulated that it is a universal force acting between all objects with mass. Every object in the universe, regardless of size, attracts every other object gravitationally. In 1687, Newton formalized this understanding with his law of universal gravitation. He described gravity as an attractive force between two masses, acting along a line connecting their centers. This law expresses a remarkably simple equation. State that gravitational force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Newton's law revolutionized our understanding of the cosmos. It successfully explained the falling of the objects on Earth, the motion of planets around the Sun, and even the tides. By applying principles of rotational motion, momentum, and centrifugal force, Newton elegantly demonstrated why planets maintain stable orbits around the Sun instead of falling into it. For over 2 centuries, Newton's framework of gravity as a force reigned supreme in scientific thought. However, it left a critical question unanswered. What is the underlying mechanism that generates this force? Furthermore, Newton's theory encountered difficulties in explaining certain anomalies, such as the subtle shifts in Mercury's orbit. These limitations paved the way for paradigm shift in the early 20th century, leading to development of Einstein's theory of general relativity, which offered a more profound and comprehensive understanding of gravity. In 1905, Einstein revolutionized our understanding of space, time, and motion with the publication of his special theory of relativity. This groundbreaking theory rests on 2 fundamental principles. Firstly, the laws of physics are the same for all observers moving at constant speeds. This means that the outcome of any physics experiment, whether conducted on a stationary lab bench or within a uniformly moving train, will be identical. Secondly, the speed of light in a vacuum is a constant, approximately 3 into 10 to the power 8 meters per second for all observers. This holds true regardless of the motion of either the light source or the observer themselves. The special theory of relativity introduces a profound and counterintuitive concept, the relativity of space and time. Observers in different frames of reference, such as a person on the ground and another in a moving spaceship, will experience space and time differently. An event that appears simultaneous to one observer may not appear so to the other. This arises from the relative motion between the two, leading to varying measurements of space and time. A key implication of this is that time is not absolute. Time dilation is a striking example of this, where time appears to pass more slowly for a moving object compared to a stationary one. Imagine 2 twins, Tom and John, each in a separate room with a clock. They agree to greet each other after 24 hours according to their respective clocks. However, unknown to John, his clock runs 50% slower. When Tom knocks after 24 hours on his clock, John is surprised because his clock only shows 12 hours. This highlights how time can be perceived differently depending on the frame of reference. This phenomenon becomes more significant when considering high speeds, such as those approaching the speed of light. If John travels in a spaceship at such a speed, everything within the spaceship, including his biological process, will appear normal to him. However, from an external perspective, time within the spaceship is dilated. This has remarkable consequences. After a 10-year space journey for John at the 99% of the speed of light, he returns to Earth to find his twin brother significantly older, perhaps even 70 years old. The stark difference in aging is a direct result of time dilation. It is important to note that this phenomenon is not just about the passage of time. Length contraction, another consequence of relativity, also affects the perception of distances for the space-bound twin, which we will explore in more detail later. Time dilation is beautifully captured in Einstein's time dilation equation. To give you an approximate idea, 1 year at 99% of the speed of light is approximately 7.09 years on Earth. Imagine a spaceship 100 meters long at rest. When the spaceship travels at a significant fraction of the speed of light, a strange phenomenon occurs, length contraction. From the perspective of a stationary observer, the spaceship appears shorter in the direction of its motion. For example, if the spaceship is moving at 90% of the speed of light, an observer on Earth would perceive it as only about 43.6 meters long. This shortening effect, predicted by Einstein's theory of relativity, is a consequence of the relative nature of space and time. However, for the astronauts inside the spaceship, nothing seems unusual. They would still measure the spaceship's length as 100 meters because they are within the same frame of reference as the spaceship. This apparent discrepancy in length is a direct result of the relative nature of space and time, and it can be mathematically proven using the length contraction formula. Einstein revolutionized our understanding of the universe by unifying space and time into a single four-dimensional continuum called spacetime. This concept recognizes that space and time are not independent entities but are interwoven and inseparable. Objects exist within their own unique slice of space-time, defined by their position in space and their moment in time. The nature of space-time is dynamic. This means that an object's motion through space alters its experience of time. Imagine space-time as a giant sheet of fabric. Now imagine you are standing at a specific point on this sheet representing an event. The light cone is like a cone-shaped boundary that extends outward from your position. The upper part of the cone, called future light cone, represents the future. Events within this region are causally connected to you. This means you can potentially influence these events, but you cannot receive information from them yet. The lower part of the cone, called past light cone, represents the past. Events within this region have already influenced you. You can perceive information from these events, but you cannot affect them anymore. Nothing can travel faster than light. So events outside the light cone are disconnected from you. This means you can neither influence them nor be influenced by them. Space-time interval represents the distance between two events in space-time. Imagine two observers in their own slice of space-time. They observe two events in space. Depending on observer's frame of reference, the spatial distance and temporal duration vary depending on observer's frame of reference. But in their own space-time, which are different from their reference frames, the space-time interval remains constant. This ensures that the laws of physics are consistent for all observers moving at constant velocities. Imagine an object existing in its own slice of space-time with position and momentum. In the absence of any substantial mass and energy, the object's space-time looks like a flat, flexible fabric without any bends or curvatures. The presence of mass and energy starts affecting the space-time fabric of the object. Imagine a bowling ball placed on a trampoline. It creates a depression in the fabric of the trampoline, right? Similarly, massive objects like stars and planets warp the surrounding space-time. This curvature manifests as gravity. Objects within this curved space-time follow geodetic paths, which are the shortest paths through the curved space. The relationship between mass, energy, and space-time curvature is represented by Einstein's field equation in a very complex mathematical equation. This equation is expressed in the language of differential geometry. It states that the presence of mass and energy warps and curves the fabric of space-time. This curvature in turn dictates how objects move within the gravitational field. Objects experiencing acceleration or deceleration within this curved space-time are essentially changing their direction within the curved geometry of space-time. Light, while massless, is still affected by the curvature of space-time. As light travels through a region of curved space-time, its path is bent. This phenomenon is known as gravitational lensing. Massive objects such as galaxies or galaxy clusters can act as gravitational lenses, bending the light from the more distant objects. This can lead to the magnification, distortion, and even multiple imaging of distant sources. Gravitational lensing provides astronomers with a powerful tool to study the distribution of matter in the universe. During a solar eclipse in 1919, astronomers observed that the light from the distant stars passing near the sun was deflected, confirming Einstein's prediction of gravitational lensing. Gravitational redshift is a phenomenon where the frequency of light decreases as it escapes from the gravitational field. As light climbs out of the gravitational wall, it loses energy, causing a shift towards the red end of the electromagnetic spectrum. This redshift is a direct consequence of the curvature of spacetime and the equivalence principle, which states that gravity is equivalent to acceleration. Gravitational time dilation is another consequence of spacetime curvature. Clocks in stronger gravitational fields run slower than those in weaker fields. This means that time passes more slowly for an observer closer to a massive object. This effect has been experimentally verified, and its implications are crucial for precise navigation systems such as GPS. Einstein's theory did not just stop at spacetime curvature, it also predicted something extraordinary: gravitational waves. These are ripples in spacetime caused by the acceleration of massive objects. Imagine two black holes spiraling toward each other. Their colossal motion sends ripples outward, much like a stone dropped in a pond creates waves. The explosive death of massive stars, called supernova, can also produce gravitational waves. For decades, gravitational waves remained purely theoretical. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting gravitational waves from the merger of two black holes. This discovery confirmed Einstein's century-old prediction and opened a new window into the universe. Today, gravitational wave astronomy allows us to study phenomena that were previously invisible, such as neutron star collision and black hole mergers. It is like adding a new sense to our observational toolkit, letting us hear the soundtrack of the cosmos. While general relativity excels at describing gravity on large scales, such as planets, stars, and galaxies, it falters when we venture into the quantum realm, the domain of the very small. Here, quantum mechanics reigns supreme, describing particles and forces at atomic and subatomic scales. What is the challenge? General relativity and quantum mechanics are fundamentally incompatible. Reconciling them into a single framework, a theory of quantum gravity, is one of physics' greatest unsolved puzzles. One promising approach is string theory, which posits that all particles, including the hypothetical graviton, the quantum carrier of gravity, are tiny vibrating strings. These vibrations give rise to different particles, including the graviton, the hypothetical particle that mediates gravity. Another approach is loop quantum theory, which envisions space-time itself as made up of discrete quantized units of loops and networks. Despite decades of efforts, a complete quantum theory of gravity remains elusive. However, research continues, driven by the hope of unifying our understanding of the universe from the smallest scales to the largest. What is the true nature of gravity? How does it connect to dark energy and dark matter? And can we ever unify it with quantum mechanics? We still do not know. Looks like the story of gravity is far from over. Thank you for watching.